Okay, so as the name suggests, system of particles consists of a system that consists of multiple particles, or more than one particles. Okay, so before we come to exactly what is center of mass of a system of particles, let's look at officially the definition of what is a system of particles, and also certain classification of system of particles. Okay. So any system consisting of multiple particles okay, is called a system of particles. And in a sense, that is a statement which is like an infinite loop, because actually uh, it's very hard to define what is a single particle. Okay, because as far as physics is concerned, we're always in the process of breaking particles into their constituent particles, so it's an endless process. Okay, so in that sense, we probably, I mean, we can definitely not call a nucleus of an atom as a single particle, because it consists of multiple particles. Cannot call protons and neutrons as particles because they can be broken into quarks. We can probably call an electron at this stage as a particle because it has not been broken yet, but okay, even that is questionable. Okay, so that statement then becomes endless. Okay, but from a mechanics point of view, I mean, from a classical mechanics or Newtonian mechanics point of view, okay, we can say that if there is a system that consists of individual lumps of mass, okay, which are in some way connected to each other, then we can call that as a system of particles. Okay. So in that sense, we can divide system of particles into two categories. Okay. One is what we call a discrete particle system. So discrete means individual, okay, and the other is a continuous. Okay. So we'll call it a continuous distribution of mass. Okay, so again, at the subatomic particle, or at least at the microscopic level, okay, there is no such thing as continuous distribution of mass. There are always individual particles which are separated from each other. But remember that we are talking at the macroscopic level, not the microscopic level in Newtonian mechanics. Okay, so we can actually differentiate between these two terms, discrete particle system and continuous mass distribution. So discrete particle system is like individual particles, or you can say, individual lumps of mass, which are somehow connected to each other, forming a system. Whereas continuous distribution is where the mass is distributed continuously over a certain geometrical space. Okay. So discrete particle systems are individual particles, okay, located at discrete. Discrete means separate, okay, individual or separate positions that are connected in some respect to form a system. Whereas continuous mass distribution is mass in the form of particles
So can you give examples?
Yes, we will take examples and understand how to also locate the center of mass of such different systems.
Okay, sir.
So basically what we see in everyday life around us is mostly continuous distribution of mass. Okay, whether we are talking about a rod, okay, or a disk, or a solid sphere, or a hollow sphere, these are all continuous distributions of mass. Whereas this is something which is a bit more abstract. Okay. Suppose we have two atoms at a fixed separation. We can treat the atoms like individual particles. If the fixed separation between them is reasonably large compared to the diameter of the atoms. Okay. So this is a somewhat abstract example of a system of two particles. So if we have, for example, a diatomic molecule, okay, then you can treat the two atoms as individual particles, and the molecule itself becomes a discrete particle system consisting of the two individual particles, which are the two individual atoms.
Okay, sir.
Understood the point? No? Yeah. Okay.
Then, sir, can a discrete particle system be made up of multiple objects with continuous distribution of mass?
We can, yeah, in a sense, it is becoming like that. Now, for example, even this abstract example that I'm taking of two atoms, okay. Now the atoms themselves also consist of particles, right?
Yes, sir.
Subatomic particles, then you can break the subatomic particles into subnuclear particles, okay. But we are clumping them together as a single particle, which we are calling it the atom, in whatever scale we are visualizing the system as, right?
Yes, sir.
So for example, the typical diameter of an atom is something of the order of an Armstrong, right? Order of magnitude of Armstrong. So we are
Yes, sir.
treating our system such that anything in that scale of Armstrong, dimensions of about an Armstrong, is treated like a particle. Okay.
Okay,
But
sir.
if those are separated by a distance which is, let's say a few hundred Armstrongs, or a micro, no, not micro will become, let's say a few hundred nanometers or something, then we are treating them as separate particles. Okay. Whereas if we had a different scale of measurement where, let's say, a Fermi would be, the size of the particle, then the atom itself would consist of, I mean, literally, millions of particles, because Fermi is the order of magnitude of the dimension of nucleus, right?
Okay, sir.
So if you talk at the subatomic level and all that, this becomes a very abstract thing, that what you can define as a particle and what is therefore a system of particles. Okay.
Sir, I
So,
got you.
right. Okay. So now a better example of a system of particles which is discrete at, let's say, the macroscopic level. The type of treatment that we are doing in this chapter, where we are looking at Newtonian mechanics. A better example of a system of particles which can be treated like a discrete particle system is something like this. That suppose we have now suppose we made a square frame that consists of very light rods. So their mass is negligible. At the corners of that, we have attached small particles. Okay. So basically very small objects which are heavier. So these are four particles which are joined together, attached to each other by four identical but massless. So again, massless in that sense is a very tricky statement, because nothing is truly massless. But we know in terms of Newtonian mechanics or classical mechanics what we mean by massless. It means very light rods. So this is an example of a four particle system, what we can treat as a four particle system. Now you can always argue that what are exactly these particles? They seem to be like tiny spheres. So if we break them down into smaller particles, they consist of molecules, those consist of atoms. So that becomes endless. Okay, but at our mechanics level, we can say that, okay, these are four clumps of mass, which are individual particles, which are somehow connected to each other, forming a system. So this becomes what we can call as, or what we can describe as, a discrete particle system. Okay, so
Okay,
for
sir.
our purpose over here, that is the difference. This is a discrete particle system. But for example, if I have a square plate, then that is an example of what is a continuous mass distribution. That plate can have uniform density, it can have non-uniform density also, it can have varied thickness. But because this is mass continuously distributed over the geometrical space, okay, which is, the geometry of the square plate over here, it's a continuous mass distribution.
Okay, sir.
So that's how we differentiate, or that's how we classify continuous and discrete particle systems. Okay. So I'll just give a minute to go through this section once. And once you've done this, now we will understand what is the meaning of the term center of mass. So any system of particles, whether it is a discrete particle system or continuous particle system, will have a particular point defined as the center of mass. Okay. Within that geometrical space where the mass is distributed, there must be a particular point which we can define as the center of mass. So that is a sort of a symmetry point. Okay. The mass distribution is in a so-called symmetrical manner with respect to one specific point within that system. And that specific point is then called the center of mass. Okay, but that's a qualitative definition. So we need to understand mathematically what is meaning of center of mass.
So noted.
Just a second, sir. Just a second.
Yeah. Okay, done now?
Yes, sir.
Okay.
Yes, sir.
So now let us come to the definition of center of mass, both in terms of first qualitatively, and then we'll see that how we develop a formula and a mathematical definition for center of mass of each type of system. Okay. So qualitatively, center of mass of a system and from now we will just call this COM, or sometimes we'll just call it CM. So this is nothing but the symmetry point for the mass distribution. It is such a point that you can say about that point, the mass distribution is symmetrical. Okay. So let us now start understanding this with examples. So for example, if we have a two particle system that consists of two identical particles of identical mass, then it totally makes sense that the center of mass should be which point? It should be the midpoint, right? Because that is the geometrical center, and the mass distribution will be symmetric with respect to it. So for a system consisting of two identical particles, the center of mass is located at the midpoint. which I have labeled here as C. Okay. But now suppose the two particles in our next example. So our next example is again a two particle system, but they are not identical. They have different masses. So now suppose the particle A is of mass m, but the particle B, let's say, is of mass 3m, and the distance between them is L. Now where should the center of mass be located?
So nearer to B.
Yes, definitely it will be nearer to B, but the question is mathematically by how much? Okay. So here what will happen is that if the mass of A is to the mass of B is how much? 1:3, right? Then to get such a symmetry point about which the mass distribution is symmetrical, the center of mass should be nearer to B in such a way that now if I say this distance is x1 from A, that is okay, and this distance is x2, then x1 is to x2 should become how much? 3:1, inverse of the masses. So that mass into distance on either side is equal.
Sir, I'm actually not able to understand what we mean by this symmetry point of mass
Yeah,
distribution.
so through this definition, it will become clearer. See, the idea is simple. Na? If the mass ratios were m is to, I mean, 1:3 like it is over here, okay, let's say it is nearer to B. But instead, if it is m is to 2m, then there is a difference between the two. Na? In both cases, the center of mass will be closer to B. But in one case, it will be even closer, in the other case, it will be less closer.
Yes, sir.
So how do we put a number on it mathematically? How much closer to B and how much further from A? So that depends on the ratio of the masses of A and B.
Yes, sir.
So for example, you can take this to an extreme. Suppose the mass of B was infinite compared to mass of A, then the center of mass should merge with B almost.
Yes, sir.
Yes.
From that we are getting a sort of a idea that mathematically how we can define the symmetry point. We can define it in such a way that if the mass ratios are m1 is to m2, then the ratio of the distances should be inverse of that. 1/m1 is to 1/m2.
So just an idea, but sir, at center of mass, if I place any mass, can I say that the gravitational force of that mass for A and B will be equal?
That is that is a conditional statement. So the point that you are talking about then is called the center of gravity, and center of gravity coincides with the center of mass, provided the gravitational field is uniform. You're getting my
Okay,
point, beta? So
yes, sir.
if this is a two particle system, for example, on the surface of the Earth or anywhere near the surface of the Earth, then both the particles are experiencing the same amount of gravitational field. So then the center of mass will be the position where the gravitational force effectively acts from. But suppose for some weird reason, particle A and particle B are experiencing some different gravitational field, then the center of mass will not coincide with the center of gravity.
No, sir, I'm saying I introduce another particle at C
Hmm.
and I take the gravitational force between that particle with A and with B.
No, because gravitational force does not depend directly on distance. Gravitational force is the inverse square law of force. No,
Yes, sir.
it is inversely proportional to. So gravitational force because of A will be proportional to 1/x1 square, and because of B will be proportional to 1/x2 square.
Then, sir, why is it?
Yeah.
Why
So
is it not inversely proportional, inversely related
no,
here?
because see, center of mass's definition is not to do with gravitation. Gravitational force is a specific fundamental dynamical force in nature. That's a different thing. And center of mass by definition is a symmetry point. That's a different thing. So how we define symmetry in terms of mathematics, we define it. So I'm coming to that definition officially what we call it. But here you sort of logically understand that the heavier B is, the closer the center of mass should go to B.
Yes, sir.
So how will we mathematically relate that? That is inverse of this ratio. If A and B's ratio in terms of mass is 1:n, then the distance ratio should have become n:1. No?
Yes, sir.
Okay. So in that case, we can say that, okay, x1 will become 3/4 of L and x2 will become 1/4 of L. Okay. So here, what this position C is therefore called, the center of mass position, it is called the weighted mean. Where weightage is given to mass. It is the weighted mean position of A and B, okay, with respect to masses. So based on this, now we can come up with a formula for a two-particle system. So now we have, a mathematical definition for a two-particle system. What is the center of mass? It is the position which is called the weighted mean of the individual positions. So for any two-particle system, the center of mass is at a position which is their weighted mean. So now in terms of coordinate geometry, we can define that weighted mean like this, that for example, if we are treating the x-axis as the axis on which the two particles are lying. So the origin is somewhere here. Now one particle m1 is located at the position x equal to x1, and another particle m2 is located at x equal to x2. Then the center of mass will be a point which we can now define by this formula. So the center of mass C is a point that divides the distance x2 minus x1 between m1 and m2 in inverse ratio of their mass. So basically, if the distance from m1 is r1 and the distance from m2 is r2, then m1 r1 will become equal to m2 r2. So, inverse ratio of their masses. Okay, so this now becomes the general definition of the center of mass of a two-particle system. Okay, we'll convert this into a vector definition next. Okay, this is a scalar definition.
Sir, what is this quantity M1 R1?
Mass into distance. So that is what we mean by saying weighted mean.
So, but what does it mean?
Mass into distance, na? Dimensionally, it is mass into distance.
Yes, sir, that I got.
So then it doesn't have any physical significance other than that. No? It's just mass into distance. So when I say that it is the weighted mean, no? It means that only, no? That mass into distance with respect to one particle is equal to mass into distance with respect to another particle. That is the meaning of the term weighted mean position. Mean position would have been x1 plus x2 by 2. It would have been arithmetic mean. So weighted mean is such that mass into distance on either side is equal.
Okay, sir.
Understood? No? It's like we are giving a weightage in terms of mean position. Right? This is actually a term from statistics, now weighted mean.
So we've done this in school.
Yeah. So there you go. So for example, if you want to find the weightage of in some in terms of something else. So let's say here, instead of M1 and M2 being masses, X1 and X2 are positions of two cities on a map. Okay. And their populations are P1 and P2. Then the weighted mean would be such a position where P1 into R1 would be equal to P2 into R2. That is, population of one city into distance from the center would be equal to population of the other city into distance from that center.
Yes, sir.
So it's the weighted mean term is a more general term, but here the weighted mean is weighted, or it is weighed in terms of what? The mass. What quantity we are giving weightage to calculate weighted mean? We are giving the weightage to the quantity mass. Hence,
Okay,
the point is with what? It is symmetrical with respect to mass distribution. You can understood?
yes, sir.
Okay. Now, to generalize this definition in context of vectors, becomes very simple really. That if we have placed our two particles in a general three-dimensional coordinate frame, XYZ Cartesian coordinate frame, then their individual position vectors are suppose R1 vector and R2 vector. So these are a mutually perpendicular XYZ coordinate frame. So now suppose we have one particle which is located with respect to our origin. It is located at position vector R1. This is where our particle M1 is located. And we have another particle which is located at some other arbitrary position vector. And you have to imagine this in 3D. It's not in a flat two-dimensional plane. So they are having all three coordinates different. So basically our R1 some x1 I cap plus x2 j cap plus x3 k cap. Sorry, x1 y1 z1. So y1 I cap plus z1 k cap. So x1 y1 z1 are the coordinates for the particle of mass m1. And similarly R2 is some x2 I cap plus y2 j cap plus z2 k cap particle m2. Then the center of mass will be some point on the line joining these two, which is doing basically what? It is dividing that line in the inverse ratio of their masses. Na? So the position of the center of mass their center of mass that is located at a position given by or we can write it as a scalar equation that RCM is at some XCM I cap plus YCM J cap plus ZCM K cap, where the individual coordinates, XYZ coordinates are such that and similarly for the Z coordinate. So this becomes the vector version of the above definition that we saw, that what is the meaning of weighted mean. So if you can see that if this distance is d1, and this distance is d2. Basically now means that m1 d1 is equal to m2 d2. Okay, so C is a point which divides the line joining them in ratio of distance d1 is to d2 such that m1 d1 is equal to m2 d2.
Sir, can you please scroll up
Yeah,
for a moment?
yes. This condition is satisfied. Yeah, right. I'm scrolling up. This part.
Yes, sir.
Okay, done.
Yes, sir.
Okay, so let's let's start with a very simple question as an application of this. So two particles A and B. So mass of A is given to us as 3 kg. Mass of B is unknown. Are placed in the XY plane such that E is at the position so find if the center of mass or AB as a system is at the origin. Very simple question, just apply the above definition and you'll understand. Okay, so interestingly, you have one definition but two unknowns here, but because it's a vector definition and we are in the XY plane, so we are dealing with two-dimensional vectors, you'll be able to find both the unknown quantities using that one definition. Yes, very good. So we can see that, right. So the answers are correct. Nitish, Abhinav, Ibrahim, Anirudh, all of you got the answers correct. Mass should be 2 kg and y coordinate of B should be -9. So it's very simple. Center of mass is at 0, 0. Okay, so XCM we use this definition. So we get 0 should be equal to 3 kg multiplied with +2. We don't know the unit of this, the coordinates, but it doesn't matter. Plus mass of B into -3 divided by 3 plus mb. So here, even though the denominator is 0, I mean is unknown, it doesn't matter because the left hand side is 0. So you get 6 minus 3 times mb should be 0. So that tells us that mb is equal to 2 kg. And we know the unit of mb is kg because the unit of these two coordinates, 2 centimeters and 2 and -3 has to be same, whether it is centimeters, meters, inches, it doesn't matter. But now similarly, YCM, now we will substitute this value over here. So this 0 is equal to 3 kg multiplied by 6 plus mb multiplied with yb. So we have this new equation that 18 plus mb yb should be equal to 0. So this is like a second equation. This was our first equation. So putting that information here, substitute this here, we'll get the y coordinate. So you can see that it is -9. Whatever the unit is, unspecified at this stage. Okay. So pretty simple stuff, as you can see, but this is an example of the definitions application. Okay. Now we come to a situation where we look at a many particle system. Okay. It is multiple, more than 2 particles. If we have that kind of system. So how we can generalize our definition now? Let's understand that. So suppose we have n particles at positions x1, x2 respectively on the x-axis. We have a one-dimensional system. You can visualize our system like this, that on our x-axis, this is the origin, we have various particles located at various points. then the center of mass will be somewhere in between over here, where this will be given by this sort of formula. Or we can write this more conveniently as a summation formula. Summation of mass into x coordinate in the numerator for the index going from 1 to n, whatever the total number of particles, divided by the total mass, which we can write as summation of mass the denominator. So this is again the same definition, but it is a weighted mean of the x coordinate of n particle system. So xcm, logically it is becoming the weighted mean of the positions, that is x coordinates in this case, of n particles. So just make a note of this concept first, then we will move on to the 3D version of this formula.
Sir,
Yes.
sir, could you please scroll up for a second as I got disconnected in between? So I just want to confirm that I didn't miss anything.
Okay. We did this question before this.
Yes, yes, sir. Sir, I did
Okay.
listen to this.
Okay, now we will convert this formula into a vector formula. Okay, if we have the n particles with position vectors r1, r2, etc. So as you can probably guess, it will be the similar formula, but summation of
Sorry, what is not clear?
Yeah, so next we will convert this to a three-dimensional vector formula, where instead of the individual coordinates on an individual axis, okay, we have the vector positions of n particles. So we have a three-dimensional system. So in a three-dimensional plane, so say we've got n number of particles all distributed like this. So M1 is at position vector R1, where R1 would be some X1 I cap plus Y1 J cap plus Z1 K cap. M2 is at position vector R2, like that. We have n particles at position vectors like this. Then the center of mass would be a specific point that would lie somewhere in this system, such that that specific point basically divides, is the weighted mean of the vector positions. So the center of mass would be somewhere here, where such that RCM, the position vector of the center of mass, will again become summation of mass, but this time into position vector divided by total mass. Okay. Or we could write this as three individual coordinate equations, that the x coordinate of the center of mass is summation mx divided by summation m. Y coordinate summation my divided by summation m. And the z coordinate is similarly summation mz divided by total mass. So the definition of center of mass is once again the same. The center of mass is a point whose coordinates are the weighted mean of the n particles. Okay, so now one very simple direct implication of this is that if we have a sort of symmetrical system, that is, we have an identical particles, okay, lying on the vertices of a polygon, then by definition, the position of the center of mass becomes the position of what we call the geometrical centroid of that polygon. For a system of n identical particles, that is, the masses are the same, the center of mass is the centroid of the polygon So basically the x coordinate of the centroid, the center of mass, becomes summation x divided by the number of particles. The y coordinate becomes summation y divided by the number of particles. And the z coordinate becomes summation z divided by the number of particles. So for example, if we have an equilateral triangle whose vertices are joined, I mean, at the vertices of this equilateral triangle, we have three identical particles of mass m each. And these are just imaginary lines. So my particles are A, B, and C. But suppose these three imaginary lines are of equal distance L. Then the center of mass will be located at this centroid, for which we'll use a different symbol now because. So G is the centroid of the equilateral triangle. That is the center of mass. But that is because there are three identical particles at the corners of this equilateral triangle. So in this case, you will see that because in the case of equilateral triangle, the altitudes, angular bisectors, and perpendicular bisectors are the same, and centroid divides these in 2:1 ratio. That is the property of an equilateral triangle. We're just making use of that over here. So now we can make use of this in solving even a situation where, we don't necessarily have symmetrical particles, but we can kind of make use of this statement. Let me explain this with another example. What exactly I'm talking about making use of this theorem indirectly. So now suppose I have a situation where I'm now talking about a two-dimensional XY plane, and in that I have some particles which are like this. I have a 2D system where, let us say, I have got the origin is actually the centroid of a regular hexagon of side length L. I'm not drawing this to scale properly, so it will not look like a regular hexagon, but just imagine that it is. Now we are placing some particles at each of these corners such that particles of identical mass are placed at these 5 points, and another one of 2m, double the mass, is placed at F. So locate this system, 6-particle system. So locate this system's center of mass. Take the length L as, suppose, something like 10 centimeters. So what are the coordinates of the system center of mass? There are a couple of different methods by which we can do this. One is we can make use of that formula of weighted mean, but we can also make use of the theorem we were discussing about earlier indirectly. And what I'll show is by doing that, we can simplify the solution of this problem a lot.
Sir, could you please scroll up for 2 minutes? Actually, I didn't note the whole thing, so.
Okay, so I hope by now we would have figured out that it's actually very simple. The center of mass will be somewhere over here. Okay. So the position of the center of mass will be at x equal to, I'll just tell you, it will be minus L by 7 comma 0. And actually it's like a one-line solution. I'll explain why. Because what you can do is you can use superposition here. If you start with a system Yeah, so if I started with a system that had it identical particles, then where the center of mass would have been? It would have been at the geometrical centroid for the hexagon, which would be this. So now this particular system, now we can just write it as a combination of two systems consisting of one particle of 6m placed at here and another particle of m placed over here where f would have been. So their center of mass would be where? Their center of mass would be at this position now.
So, but the distance between them is not L, it's 3 by 2L.
No, it is L. Because hexagon, no, beta. It divides into 6 equilateral triangles.
Yes, sir.
Okay. So this is like one very simple way of doing the question, that you think of these 6 particles as a superposition of 6 particles of identical mass plus another particle of the same mass superimposed on plus another m placed at f. So this is this, okay, and that other m placed is here. So this thing now becomes equivalent to plus the additional particle m placed at f. So the center of mass would be at x equal to minus L by 7, because the center of mass would divide FO in 6:1 ratio. People, you understanding this? Anybody has a doubt with this concept over here, how we are using superposition?
Sir, I didn't understand how did you take 6m at origin?
Okay. So what, first of all, I'm saying is that you divide the 6-particle system of 5 particles of M and 1 particle of 2M. You split that particle of 2M mentally into 2 individual particles of M and N. This point is clear?
Yes, sir.
Okay. So now you start with the 6 identical particles. So forget about the 7th one of mass M at F. If I have 6 particles of identical mass M placed on this hexagon's vertices, where is the centroid?
Will be at origin.
At the origin. And where will be the center of mass? It will coincide with the centroid because the 6 particles are identical.
Yes, sir.
Understood now? So that system of 6M has its center of mass where? At the origin.
Acha, okay, sir. Okay, got
Okay,
it.
so I can treat, for the purpose of center of mass, I can treat it equivalent to a single particle of mass 6M, but that single particle should be placed where? At that system center of mass. Okay, now?
Yes, sir.
Okay. Now we can test this by just using coordinate geometry also, though that will be a bit lengthy. Okay. So we can also individually find the coordinates of each of these. No? That's also not so difficult. Just a matter of bit of patience. Okay. You just work out the geometry of this hexagon in terms of coordinates. You can do that also. Okay. But as I was saying, that's not necessary to do at all over here. We can just do one thing. Let's make life easier. Anyhow, so something like this. So if we locate the individual coordinates of all of these, you can do that also. These angles are 60 each, no? As are these angles. And all of these sides are L each. So you can see that now when I place particles like this one is 2m. So A has a mass m. Now A is located at what kind of position? This will become minus L by 2, and the y coordinate will become root 3 by 2L. Similarly, B is at a symmetrical position, L by 2, root 3 by 2L. C is at a very simple position, L comma 0. B is also symmetrical to B. E is symmetrical to B or A or whichever. But F has a mass of 2m. Like this. So now when we want to find the position of the center of mass, summation mx divided by summation m. So summation mx you will see will become, and it should be fairly easy to work this out. You'll be left with these two will give us 0. Okay. A and B together will give us summation mx 0. Similarly, C and F will give us 0. Okay. And similarly, D and E will give us, sorry, C and F will give us minus ml. And divided by the total mass, which will become 7m. So minus L by 7. Whereas the y coordinate, when you do this, you can see that A and B together are giving root 3 ml. D and E together are giving minus root 3 ml, and C and F are having 0 contribution. So it will be 0. So the center of mass, as expected, is at minus L by 7 comma 0. But the superposition method was so much faster because we just made use of the symmetry that if we split the particle F into two individual identical particles of M and M, then we have that supersymmetrical system of 6 identical particles at the corners of a regular hexagon. And then we have an additional 7th particle. So we can make use of that symmetry.
So can you scroll up once the superposition method?
So this is the formula-based method. Whereas in the above solution that I'm coming to, I made use of superposition and the symmetry concept. So this is superposition. And symmetry. How did we get the minus L by 7? Okay. So Bhavika, see what is happening in this now. In the superposition method, I've split it into a regular hexagon plus a 7th particle of M. So the
Yes, sir.
regular hexagon I've replaced with an equivalent single particle, but its mass should be how much? 6m,
Yes, sir.
and its position should be at the origin. And the seventh particle is located at where? At minus L comma 0. So the center of mass will
Okay,
divide
okay, sir, understood. Yes, sir.
in 6:1 ratio. So this distance from the origin will become 1/7 of that. So the distance is L by 7 and the coordinate is negative.
Yes, sir.
Okay, so like that here, for example, instead of F or C, if I had replaced one of the other particles like A, V, D or E with 2m, then it would require a little bit more extra work, because you would have to find the coordinates of that point with respect to the origin. And then that line joining those two, origin and that point, would be divided in 1:6 ratio. But still superposition would still make things simpler compared to just, brute force using the formula method. The brute force formula method is not required in this case because the masses are not different. Had all the 6 masses been different, then probably this method would have been the simpler method of the two. Okay, people. So with that, we come to an end of today's session. Okay, so we haven't really, made that much progress in center of mass today. So do some reading of center of mass from Resnick Halliday, and you can start with some examples from H.C. Verma. I'll send you a list of questions also. I will also send a revision exercise in circular motion. That is assuming you people have finished the module in circular motion. So please complete the module questions, and also don't forget to do circular motion questions in H.C. Verma's chapter of work by energy. Okay, not just the circular motion chapter, but the work by energy chapter has a lot of vertical circular motion questions where conservation of energy has to be used. So make sure you do those questions and send me any doubts, etc. that you have. Okay. Yes, Dhruv, you had a question?
Yeah, sir, could you please scroll up to that note thing that we
Yeah. Now, almost every center now you're having physical doubt sessions. Okay. So for example, this week, personally, I'm going to be there for doubts in Nerul, North Point, as well as Thane. Okay. Next week, probably Kharghar. Okay. Next week, definitely Kharghar. So, but anyway, there will be other teachers taking physics doubt sessions in all the centers this week. So also try to cover your your circular motion doubts during the physical doubt sessions as much as possible. Okay. And if anything is pending, send it to me on WhatsApp. Okay. If required, I will even help you out through a Zoom session or help you out by sending some hints, etc. on WhatsApp. Okay. But as much as possible, start clearing your doubts during the physical doubt sessions from this point onwards. Okay. Because there are going to be regular physical doubt sessions in all subjects, in all centers.
Thank you, sir.
So, sir, above this, not this one, the center.
Achha. This one?
Yes, sir. Yes, sir.
Okay. Okay, people. So that's it for today's session. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir.
Thank you so much.
Bye, sir. Thank you.
Thank you, sir. Bye, sir.